Alright, think back to the beginning of the year when we were dealing with translational kinematics. Um, the kinematics explained the very basics as far as what's happening there, but they didn't explain why that object was accelerating. Right? It took until Newton's second law for us to be able to actually detail what exactly is causing these accelerations. So torque is kind of in the same boat. Torque is the rotational analog of force, meaning that torque explains why an object rotates as it does. So, for instance, let's take a look at this image. We've got four different forces acting on this door. Now, test it out on a door in your home, or, just use common experience. Which force is most easily going to open the door? Well, force 1, obviously, right? Now, force 4, it will open the door, but you're going to have to apply a larger force than force 1 in order to get that door to rotate. Same thing with force 3. If you push on it at an angle, right, you're going to have to exert a larger force than you would if you exerted it like force 1. Now, force 2, if you're pushing directly at the hinge, that door is never going to rotate. So, the ability of a force to cause a rotation is going to depend on three things. It's going to depend on the size of the force, the magnitude. It's going to depend on the angle at which you apply that force. And it's going to depend on how far away from the actual pivot, the center of rotation, you're applying that force. And that's what we call torque. And so torque is taking into account all three of these factors in order to explain why rotation occurs as it does. And it just comes from the Latin for torquere, which is to twist. Now, there are two different ways to find your torque, but they both depend on finding some sort of perpendicular relationship between a distance from the hinge and the force. Right? So the two main equations we're going to look at, and this is the Greek letter tau, that's going to represent torque. It could be a perpendicular force applied to a radial line, or a force applied to a moment arm. And that will make sense in a second here when we start to look at some of these images. But again, the key thing here is, even just without understanding necessarily what this equation means right now, is that there's got to be some perpendicular relationship between a force applied and some distance from the center of rotation. Now, the first way we can look at it is in terms of looking at a radial line. And a radial line would be a direct line from the pivot point straight out to where the force is applied. Now, if you have a force applied at an angle, so if we're looking at this example of a wrench trying to turn a nut, only forces that are perpendicular to that radial line will actually contribute to any rotational motion, right? So if you break it down, right, into F perpendicular and F parallel, well, the only portion of this force that is contributing to the rotation of the wrench itself is going to be that perpendicular component of force, right? If you look at the parallel component of that force, right, just imagine just pulling backwards on a wrench. If you're pulling backwards on a wrench, you're never going to actually turn that wrench. So only these perpendicular components of a force to the radial line will contribute to any sort of rotational motion. And so if we're looking at it in terms of a radial line, right, only the perpendicular component of your force contributes to the overall torque. Now your torque is going to be measured in Newton meters, right? Force measured in newtons, radius measured in meters. Now the secondary way we can find torque is if we do what we call line of action. So if we're looking at that same image as we did up here, A line of action means that we extend that force vector on either side to infinity, right? So you just take yourself a ruler and you expand that vector on either side to infinity. Now, what you want to do then is look at taking a ruler, placing it on the pivot, and you're trying to find a straight line that intersects perpendicular to that line of action. And that's what we call the moment arm, right? And so in that case, we're looking at your force, your overall force, and that moment arm, that line from the pivot that intersects perpendicularly to that line of action, and that will give you your torque. Now, you're going to see this equation, the torque equals Fr sine phi, on the equation page. I highly recommend you ignore that because that angle phi that they give you is not necessarily going to be a sine function. Right? So focus on instead these perpendicular relationships, either with the moment arm and the line of action, or the radial line and the perpendicular component of force to that radial line. Right? So make it easier on yourself and just do the extra legwork. Don't trust that it's going to be a sine function necessarily, because we're going to see this in a few minutes. A lot of these are actually going to end up being cosines. So there's that. Alright, so just like with kinematics, or rotational kinematics, when the torque causes the object to rotate counterclockwise, it's positive torque. If it causes it to rotate clockwise, it's negative torque. Right? So again, think back to the unit circle. If it's counterclockwise positive, clockwise negative. So if we're looking at this image here, this force would generate the maximum positive torque. This force would generate the maximum negative torque. This would be some amount of negative torque. This would be some amount of positive torque. And these two that are directly parallel to that radial line would generate no torque at all. Right? If you push on the wrench or pull on the wrench, that wrench isn't going to spin. So take a look at example 7-8. It is hard to get going if you try to start your bike with the pedal at the highest point. Why is this? Well, if you're trying to start your bike with the pedal at the highest point, so let's say this is your pedal and this is the gear. Well, if you push straight down with some amount of force, that pedal's not going to spin. Right? So if you want to get your bike going from this position, you've got to exert a very large force at an angle on this pedal. And only the perpendicular component of that force is actually going to contribute to the rotation of the pedal itself. My apologies, I misdrew that. So only the perpendicular component of that force to the radial line is actually going to contribute to the actual spinning motion. Right? So that's why ideally, if you can start your bike like this and deliver a large force straight down, you'd get the maximum amount of torque generated within the cycle itself. So let's take a look at example 7-9 in the notes. Here we've got Ryan, who is trying to open a stuck door. He pushes on it at a point 0.75 meters from the hinges with a 240 Newton force directed 20 degrees away from being perpendicular to the door. There's a natural pivot point, the hinges. What torque does Ryan exert? How could he exert more torque? So they give us a nice little image here. Right, we know the radial line is 0.75 meters. We know that that force is directed 20 degrees from the perpendicular. And we know that only this perpendicular component of the force is actually going to assist in any rotational motion. So our radial line, is 0.75 meters. Our perpendicular component of our force is going to be the force, and in this case, it's going to be the cosine of 20. Alright, so 240 newtons times the cosine of 20 degrees. Make sure your calculator is in degrees and not radians. And you get 225.5 newtons. So this is the only amount of that 240 newtons worth of force that actually contributes to that door being rotated. So if we want to find the torque is equal to our perpendicular component of force times the radial line. All right, so torque is equal to 225.5 newtons times 0.75 meters, which comes out to 169 newton meters. Now the second part of the question is, how could he exert more torque? Well, the easiest way to exert more torque would be, instead of exerting a force on the door that looks like this, right, he could exert a force on the door that looks like that. So if he applied equal amount of force, but applied it straight or directly perpendicular to the door itself, then he would exert more torque, and the door would rotate. Now, take a look at Stop to Think 7.3. We've got a wheel. It turns freely on an axle at the center. Which one of these forces will provide the largest positive torque on the wheel? So go ahead, pause the video, see if you can't come up with that answer. Well, the answer is E. Right? E is the only one that will E is the only force that will force this wheel to rotate counterclockwise. Right? So it's going to be the only force that will give you a positive torque. Now, if the question was just what provides the largest torque in general, then A would be the answer. Right? A provides a very strong torque, but its clockwise is negative. B will also spin it clockwise, and C and D will generate no torque at all because you're basically just pulling at the wheel. So let's take a look at example 710. Here we got Luis uses a 20 centimeter long wrench to tighten a nut, turning it clockwise. So if he's turning it clockwise, then that torque is going to be negative. The wrench handle is tilted 30 degrees above the horizontal, and Luis pulls straight down on the end with a force of 100 newtons. How much torque does Luis exert on the nut? Now, take a good look at both A and B in figure 722. Basically, what they've done is they've set this up for you in both different ways. So in this case, they've set it up for you with the radial line and your perpendicular force to that radial line. And they've also set it up in B as your line of action and your moment arm. So it doesn't matter which way you solve the equation. What really matters is that you are seeing this perpendicular relationship between a force and some distance from the center of rotation, the pivot point, the axis. So let's go ahead and solve it out both ways. So let's solve it out using the method shown in A in figure 722. So we've got ourselves a radial line of 0.2 meters. We've got ourselves a perpendicular force, right? That would be equal to the force times the cosine of 30 degrees in this case, right, which would be equal to 100 newtons. times cosine of 30 degrees. So our perpendicular force here comes out to 86.6 newtons. So if we want to find the torque, it's your perpendicular component of the force times that radial line. So your torque is equal to 86.6 newtons times 0.2 meters, right, which gives us 17.3 Newton meters. So now let's look at it from the other perspective. Now in B, we're looking at the line of action and the moment arm. Now our force in this case is 100 newtons. Now we know that there is a radius on that wrench of 0.2 meters. And that moment arm intersects that line of action at a 30-degree angle. So this right here represents our moment arm. So our moment arm, right, can be found by taking the hypotenuse of this triangle, the 0.2 meters, and multiplying it by the cosine of 30 degrees. So our moment arm is 0.2 times the cosine of 30, which comes out to 0.173 meters. So there's a 0.173 meters between the pivot, the nut that the wrench is working on, and that line of action. So if we want to find the torque in this case, well, it's the force times that moment arm. So torque would be 100 newtons times 0.173 meters. Right, so your torque comes out to 17.3 Newton meters. Right, so it doesn't matter which way you go about solving this. Either way, you end up with the same answer. So again, the key there is finding that perpendicular relationship between a force and a distance. And so lastly, let's take a look at example 711. Now, a capstan is one of these mechanisms in old ships where the sailors would push on them and raise the anchor. So in this case, we've got ourselves a net torque of 0. And we'll get into net torque here in the next video. But for now, just recognize that net torque means that the object is either being spun at a constant angular velocity or that it is not rotating at all. So suppose the rope tension due to the weight of the anchor is 1500 newtons. If the distance from the axis to the point of the lever where the sailors push is exactly 7 times the radius of the capstan, with what force must the sailor push if the net torque on the capstan is to be 0? So they've given us a nice little free body diagram here. Right, so here, this tension, T, that's the weight of the anchor pulling down on the capstan. And then F here is the sailor pushing it. Now notice, we don't have to worry about angles at all in this case, and generally speaking, most of the time, you don't have to worry about an angle because most of the time they're going to be giving you a force that is perpendicular to the radial line to begin with. So we want to know how much force he needs to apply in order to rotate this at a constant velocity. So in this case, we're told that the net torque is 0. Meaning that our net torque is equal to the counterclockwise torque, which would be positive, minus your clockwise torque, which would be negative, and they cancel each other out. Now, if we look at the image again, the sailor is providing a clockwise torque, right? So he's going to be negative. And the tension force, the force that is due to the weight of the anchor itself, right, would be the counterclockwise, that would be the positive torque. So if we go through this equation, right, your net counterclockwise torque is equal to your net clockwise torque. So our counterclockwise torque is the tension in the rope times that distance from the center of rotation, r. Your counterclockwise is the force exerted by the sailor times the distance, which is 7r. Now, we weren't given what r was, but it doesn't matter because that cancels. Right, so we get that the tension is equal to 7F. So 1500 newtons is equal to 7 times whatever the force that the sailor is exerting. So plug that in, and you get 214.3 newtons. Right, so the further you are from the center of rotation, the less amount of force you need to apply to cause something to rotate. And we'll get into that more in the next video. I've uploaded some basic torque questions. Take a look at them, and I will see you all soon.